Properties of the empty set. So we've started a new section on the properties of the empty set. Now, you might be thinking, the empty set, isn't that just nothing? And you're right, in a way. But even though it seems simple, the empty set actually has some really important characteristics that form the foundation of how we work with sets in mathematics. These properties aren't just there to make things complicated. Understanding them is crucial if you want to confidently work with sets and perform operations like unions, intersections, and more, things we'll definitely be covering. Think of it like building with Legos. You need a solid base before you can start constructing anything complex. The empty set and its properties are that base for set theory. Over the next few slides, we're going to explore these properties in detail, one by one. We'll look at what makes the empty set unique and how it behaves in different situations. So, let's dive in and start uncovering these fundamental concepts. Cardinality of the empty set. So we've just started looking at the properties of the empty set, and now we're going to talk about something called cardinality. Cardinality, simply put, refers to the number of elements that are in a set. Think of it as counting how many things are inside the curly braces that define the set. For instance, if I have a set containing the numbers 1, 2, and 3, that's written as 1, 2, 3 with curly braces around it. Then that set has a cardinality of 3 because there are 3 elements within it. Now let's apply this to the empty set. Remember, the empty set, which we represent as either the empty curly braces or with a special symbol that looks like a capital O with a slash through it, contains absolutely no elements. It's, well, empty. Therefore, if we want to know its cardinality, how many elements are in it, the answer is 0. We have a special notation to represent cardinality. We write the name of the set, for example, A, and then a vertical bar on either side of it. So that's read as the cardinality of A. Therefore, specifically for the empty set, we can write that the cardinality of the empty set is equal to 0. That's written as the symbol for cardinality of the empty set equals 0. Now you might be thinking, this seems really obvious. And you're right, it is a simple concept, but it's incredibly important. This establishes a baseline for how we count elements in all sets. It's a foundational idea that we'll build upon as we explore more complex set theory concepts, like set operations, which we will cover in the following slides. So, make sure you understand this one well. The empty set is a subset of every set. This slide introduces the concept of a subset. A subset of a set, let's call it A, is simply a set that contains only elements that are also found within the original set, A. We use a special symbol to denote this, B subset of A, which we would read as B is a subset of A. Now here's a key idea. The empty set is a subset of every set. This might sound strange at first, but it's a fundamental principle in set theory. Let's think about it logically. Imagine we have any set A, and we want to determine if the empty set, which we've been representing as a symbol with nothing inside, or simply as empty set, is a subset of A. To prove that the empty set is indeed a subset of A, we need to demonstrate that every element within the empty set is also present in A. But here's the crucial point. The empty set has no elements. Because there are no elements in the empty set to even check, the condition for being a subset is automatically, or trivially, satisfied. There's nothing in the empty set that isn't in A, because there's nothing in the empty set at all. So we've just established what cardinality is, essentially, the number of items in a set. Now, let's move on to a really important property of the empty set. This is a powerful concept, and it will become very useful as we move forward with more complex set operations like unions and intersections, which we'll explore in the following slides. So, make sure you understand this one well. The empty set is a subset of absolutely any set you can think of. Examples of empty set as a subset. So let's solidify our understanding of the empty set being a subset of every set with a couple of examples. Here, we have our first example. Let's consider a set A, and we define it as containing the elements 1, 2, and 3. We write this as A equals the set containing 1, 2, and 3. The question is the empty set a subset of A? Now, remember from the previous slide, to prove that one set is a subset of another, we need to show that every element in the first set is also present in the second set. But the empty set, by definition, has no elements. So, all of its, which is 0, elements are also in A because there are no elements in the empty set to even check. The condition for being a subset is automatically satisfied. Therefore, the empty set is a subset of A. Let's look at another example to reinforce this. This time, let's define a set B as containing the elements of B, C, and D again. The question is the empty set a subset of B? The logic is exactly the same. Since the empty set has no elements, all of its, again, 0 elements are also found within set B, so the empty set is indeed a subset of B as well. And the key takeaway here is that this isn't just true for these specific sets, A and B. This property holds true for any set you can think of. The empty set is a subset of absolutely every set. This might seem a little strange at first, but it's a fundamental property that we'll use as we move forward with more complex set operations, like unions and intersections, which we'll explore in the following slides. The empty set is a proper subset of every non-empty set. Let's move on to the next important property of the empty set. As we've just established, the empty set is a subset of every set. Remember that from the previous slides. Now, we're going to refine that idea a little bit and introduce the concept of a proper subset. A proper subset is simply a subset that isn't identical to the original set. So, if we have a set A, a proper subset of A would be a set containing only elements found in A, but it cannot be A itself. It has to be strictly smaller. Now, think about the empty set. We know it has no elements at all. And consider any other set, let's call it a that isn't empty. That means A has at least one element, right? Because the empty set has no elements, it can never be equal to a non-empty set. Therefore, since the empty set is a subset of every set, and it's never equal to any non-empty set, it's always a proper subset of any non-empty set. This is a subtle but important distinction. We'll see how this plays out when we look at set operations like union and intersection in the slides to come, so it's good to have a firm grasp on this now. Example of empty set as a proper subset. Let's look at a concrete example to solidify our understanding of proper subsets. As we discussed on the previous slides, the empty set is a subset of every set. Now, we're taking that a step further to define what a proper subset is. Remember, a proper subset is a subset that isn't equal to the original set itself. So, on this slide, we have a set A, defined as containing the elements 1 and 2. We write that as A equals the set containing 1, 2. Now, let's consider the empty set. We've already established that the empty set is a subset of A, meaning all of its elements, which, of course, are none, are also found within A. The slide also points out that the empty set is not equal to A. A contains 1 and 2, while the empty set contains nothing at all. Because the empty set is a subset of A, and it is not equal to A, we can confidently say that the empty set is a proper subset of A. This example is important because it highlights the distinction between a regular subset and a proper subset. It reinforces that the empty set fulfills the criteria for being a proper subset of any non-empty set, which we'll continue to explore in the following slides. Keep this in mind as we move forward, because understanding proper subsets will be crucial when we start looking at more complex set operations. The empty set is the subset of itself. Let's move on to a slightly unusual but important property of the empty set. Now, on this slide, we're looking at something that might initially feel a little strange, the empty set being a subset of itself. As the slide points out, this can seem counterintuitive. We've just established that the empty set is a subset of every other set, and now we're saying it's a subset of itself. It sounds a bit odd, doesn't it? But it's actually a direct result of how we define a subset. Remember, for a set to be a subset of another, every single element in the first set must also be present in the second set. Now, consider the empty set. It has no elements. Therefore, the condition for being a subset of itself is, well, trivially met. What that means is, we're saying every element in the empty set is also in the empty set. And because there are no elements in the empty set, there's nothing that can disprove that statement. There's no element we can find in the empty set that isn't also in the empty set, simply because there are no elements at all. Think of it this way. The definition doesn't say, at least one element, it says every element. Since there are 0 elements, the every condition is automatically satisfied. This might feel like a technicality, but it's a logically sound consequence of our definitions, and it's important to understand for more advanced set theory concepts. We'll be building on these foundational ideas as we continue, so make sure you're comfortable with this one before we move on to how the empty set interacts with set operations like union and intersection, which we'll cover in the following slides. Union with the empty set. Now, this slide introduces the concept of the union of two sets. The union, which we denote as a union B, is essentially combining all the unique elements from both set A and set B into a single set. So, it includes everything that's in A, everything that's in B, and avoids any repetition. The slide then focuses on what happens when we take the union of any set. Let's call it A, with the empty set, which we've been denoting as phi, or just using curly braces to represent it as an empty set. The crucial point here is that the result of this union is simply the original set, A. We write this mathematically as a union phi equals A. Think about it logically. The empty set, by definition, contains nothing. When you combine a set A with something that has no elements, you don't add anything new to set A, it remains unchanged. Therefore, the union just gives you back the original set. Let's move on to another important property involving the empty set. As we've established, understanding how the empty set interacts with other set operations is key to mastering set theory. This might seem obvious, but it's a fundamental property that simplifies many set operations, and we'll see how this comes into play when solving more complex problems. In the next slide, we'll look at a similar operation, the intersection, and see how the empty set behaves in that context. So, keep this idea of the empty set contributing nothing to a union in mind as we move forward. Example of union with empty set. Let's look at a concrete example to solidify our understanding of how the empty set behaves when we perform a union. As you can see on the slide, we're given a set A, which contains the elements 1, 2, and 3. We can represent this as A equals the set containing 1, 2, and 3. And of course, we have our empty set, which we've established contains absolutely nothing. Now we're going to find the union of A and the empty set. Remember, the union combines all the unique elements from both sets. So, a union the empty set means we take everything in A, everything in the empty set, and put it into a new set. But since the empty set has nothing in it, adding it to it doesn't change at all. Therefore, a union the empty set simply equals A, which is the set containing 1, 2, and 3. This demonstrates a key property. The empty set doesn't contribute any new elements when you take its union with another set. It's like adding 0 to a number. It doesn't change the value. In the next slide, we'll explore what happens when we take the intersection of a set with the empty set, and you'll see a similar principle at play. So, keep this example in mind as we move forward. It really highlights how the empty set acts as a sort of neutral element in set operations. Intersection with the empty set. Let's move on to another important operation involving the empty set. This slide focuses on the intersection of sets. Now, remember when we talked about the union of sets, combining all the elements? The intersection is the opposite. The intersection of two sets, let's call them A and B, is a new set that contains only the elements that are present in both A and B. We represent this intersection with this symbol. A with a little upside-down U inside, that's read as a intersection B. So, a intersection B is the set of all elements that A and B have in common. Now here, S where the empty set comes in. What happens when we take the intersection of any set? Let's stick with A and the empty set. Well, the result is always the empty set itself. We write this as A intersection empty set equals empty set. Think about it logically. The empty set, by definition, contains no elements. Therefore, there's absolutely no way for any elements to be common to both set A and the empty set. Since there are no elements in the empty set, there can't be any elements that are in both sets. This might seem simple, but it's a crucial property to understand as we continue working with set theory. We'll see how these basic properties, like the behavior of the empty set with union and intersection, build up to more complex concepts. In the next slide, we'll look at an example to solidify this idea. Example of intersection with empty set. Let's look at another example to solidify our understanding of how the empty set interacts with set operations. This is slide 11, and it focuses on the intersection of a set with the empty set. Here, we are given a set A, which contains the elements 1, 2, and 3. We can represent this as A equals the set containing 1, 2, and 3. And of course, we have the empty set, which we've established contains no elements. It's just a set with nothing inside. The slide then shows us what happens when we find the intersection of A and the empty set. Remember, the intersection of two sets means we're looking for elements that are in both sets. So, A intersection empty set equals the empty set itself. This is because when we examine set A and ask what elements it shares with the empty set, there are simply no elements in the empty set to share. Therefore, the resulting intersection is also an empty set, a set with no elements. This reinforces what we learned on the previous slide. The intersection of any set with the empty set always results in the empty set. It's a direct consequence of the definition of intersection. Now, after this, we'll wrap up with a summary of the key takeaways from all these properties of the empty set. So make sure you've got a good grasp of these examples before we move on. Key takeaways. First, remember that cardinality refers to the number of elements in a set. We established that the empty set, by definition, contains no elements. Therefore, the cardinality of the empty set is always 0. We write this mathematically as cardinality of the empty set equals 0. Next, we proved that the empty set is a subset of every set. Think about it, to be a subset, all elements of the first set must be in the second set. Since the empty set has no elements, this condition is automatically true for any set we choose. Interestingly, the empty set is also a subset of itself. This might seem strange, but it follows directly from the definition of a subset. Again, because there are no elements in the empty set to contradict this, the condition holds. Now, let's consider set operations. We saw that when you take the union of any set with the empty set, you simply get back the original set. Remember, the union combines all unique elements. Since the empty set has no elements, it doesn't change the original set at all. Finally, when you take the intersection of any set with the empty set, the result is always the empty set. The intersection finds elements common to both sets. Because the empty set contains no elements, there can be no common elements, leaving us with the empty set. Let's recap everything we've learned about the empty set. This slide, titled Key Takeaways, summarizes the most important properties we've covered. These 5 points are fundamental to understanding the behavior of the empty set in set theory. Keep these takeaways in mind as we move forward, because they'll be crucial for solving more complex problems. On the next slide, we'll address some common mistakes students make when working with the empty set, so you can avoid those pitfalls. Common mistakes. The first point here is about confusing cardinality with the set itself. Now, remember we talked about cardinality earlier. It's simply the number of elements within a set. So, if I say the cardinality of a set A is 3, that means set A contains 3 elements. The empty set, as we've established, contains no elements. Therefore, its cardinality is 0. It's crucial to remember that the empty set, written as a symbol resembling a 0 inside curly braces, is the set itself. It's a container. The cardinality, written as vertical bars enclosing the set symbol, is the number of things inside that container. So, the empty set is not 0, it has a cardinality of 0. Don't equate the set with the number of elements it holds. Now, the second point addresses a concept that often trips students up, the idea that the empty set is a subset of every set. It feels strange, right? How can something with nothing in it be contained within other sets? Well, let's revisit the definition of a subset. For a set B to be a subset of a set A, every element in B must also be in A now. Think about the empty set. It has no elements. Because there are no elements in the empty set to check, the condition for being a subset is automatically satisfied for any set you choose. It's a bit of a logical trick, but it's fundamental to set theory. So, don't get hung up on visualizing it, focus on the definition. Let's move on to this final slide, which highlights some common mistakes students make when working with the empty set. Understanding these pitfalls will help solidify your understanding. These are the two most frequent areas where students stumble, so pay close attention to them. Now that we've covered these common mistakes, you should have a solid grasp of the properties of the empty set and be well equipped to tackle more complex set theory problems.